And I believe that we need an international organization that will make policy decisions about such an object. We are worried about existential threats from artificial intelligence.
NASA's new dataset just rewrote the rulebook, because 3I/Atlas, billed as a comet, won't behave like anything natural. Its chemistry is all wrong, its lights flicker in ways never seen, and experts admit its path through our solar system defies cosmic odds. At over 130,000 miles per hour, the third interstellar visitor is now the most mysterious. Too dense, too fast, and overwhelmingly alien in every measurable way. Headlines scream alien craft, while scientists scramble for explanations that don't fit. But if it really is technology from another star, the stakes go far beyond speculation. The next 8 minutes will reveal why 3I/Atlas has broken every expectation, and what its impossible features might mean for us. In standard comet science, the composition of a coma is as close to a fingerprint as nature gets. Water vapor dominates, with carbon dioxide usually trailing far behind. But for 3I/Atlas, the first spectroscopic sweeps from NASA's SPHERICS mission in July 2025 reported something outlandish: carbon dioxide vapor in amounts no comet textbook would predict. Some headlines ran with an 8-to-1 ratio of carbon dioxide to water, a number that would place 3I/Atlas in a category of its own, bordering on the unthinkable. Even among the strangest comets from the Oort cloud, carbon dioxide rarely overtakes water, and never by this margin. For planetary scientists, this was like finding a lake where there should only be a puddle. Yet, as the data poured in, the story grew more tangled. The official SPHERICS statement hedged its bets: very large amounts of vaporized carbon dioxide gas, but no published numbers, no peer-reviewed confirmation of that extreme ratio. Astronomer Carey Lisser, brought in by NASA, insisted the readings could still fit the edge cases of natural comet chemistry. But the speculation didn't stop there. European telescopes, including the VLT, flagged hints of atomic nickel and cyanide gases in the coma, rare finds even for the most volatile rich comets. Nickel vapor first suggested on July 20th, and cyanide, tentatively detected by August 14th, both raised eyebrows. In classical comet science, these elements appear only in trace amounts and usually signal dramatic, short-lived outbursts. Their presence in 3I/Atlas, if real, would require either a violent surface or an unusual internal process. But the search for confirmation hit a wall. No public spectra, no line strengths, no calibration logs, just press releases and rumour. When independent teams reanalyzed the available data, they found only upper limits, not robust detections. The signature bands for nickel and cyanide simply weren't there at the required confidence. What remained was a coma dominated by dust and a red, featureless spectrum. More asteroid than comet, more mystery than answer. No clear evidence of engineered materials, no smoking gun for alien technology. And yet, the sheer abundance of carbon dioxide, even at the low end of estimates, kept the debate alive. If 3I/Atlas is natural, it is an outlier. If it's not, it may be the first object to force a rewrite of what chemistry is possible between the stars. The numbers may be uncertain, but the unease is real. Every new spectrum challenges what astronomers thought they knew about interstellar visitors. For now, 3I/Atlas sits in limbo. Its chemistry neither fully explained nor entirely unprecedented. The next anomaly would not come from its makeup, but from the way it lit up against the darkness of space. Then came the light that shouldn't have been there. As astronomers tracked 3I/Atlas through the inner solar system, the James Webb Space Telescope began registering patterns, brief, sharp flickers in the object's brightness. These weren't the slow, swelling outbursts familiar from icy comets, nor the chaotic glints of tumbling asteroids. Instead, the light curve showed a series of abrupt, sometimes clustered spikes, each lasting from a few minutes up to nearly an hour, scattered across several observing nights. In standard comet science, surface activity is a messy affair: random jets, unpredictable eruptions, sunlight coaxing vapor from hidden pockets of ice. But with 3I/Atlas, the distribution of these flickers defied that randomness. Some occurred in repeating intervals, clustered near the same rotational phase, as if certain patches on the surface were reflecting or emitting light in a deliberate rhythm. Hubble and JWST teams compared notes, ruling out cosmic rays, detector glitches, and background stars. The signals persisted, surviving every round of artifact checks. The amplitude was striking. At times, the object brightened by a full magnitude, enough to stand out even against the glare of its own coma. Color data from JWST hinted at subtle shifts during the spikes, with infrared readings suggesting a component not easily explained by dust. No clear jets, no evidence of fragmentation, just a stubborn pulse of light with no obvious source. Some researchers reached for familiar explanations, perhaps a patch of unusually reflective minerals, or a crust of crystalline ice catching the sun at just the right angle. Others pointed to the possibility of metallic surfaces, panels perhaps, or engineered facets rotating into view. In private, a handful of theorists wondered aloud about energy sources beneath the surface, systems capable of releasing bursts of power on command. No one could say for certain. The data lacked the millisecond precision needed to prove a technological signature, and yet the cadence of these events refused to settle into the noise. For those watching the numbers scroll by, it was like hearing a code tapped out in a language no one quite understood, an invitation or a warning, flickering in the dark. Trajectory, for most comets, is a game of cosmic pinball, random, chaotic, shaped by the invisible hand of gravity and chance. Yet when the first orbital solutions for 3I/Atlas were published, the numbers did not fit the familiar mold. Its path traced a line almost perfectly along the ecliptic, the same flat plane carved out by the planets and most major asteroids. Not a wild, plunging angle, but a near-planar glide, within 5 degrees of the solar system's disk. For planetary scientists, this alignment was less like a dart thrown blind and more like a deliberate shot aimed at the bullseye. Monte Carlo simulations run by teams at the Initiative for Interstellar Studies generated millions of hypothetical interstellar arrivals. The odds that any one object launched from the galactic field would enter the solar system within 5 degrees of the ecliptic. Just under 9%. Not impossible, but rare enough to make astronomers pause. And that's before accounting for the way survey telescopes, with their gaze fixed mostly on the ecliptic, skew the statistics even higher. Still, this is not the path expected for a random wanderer from the stars. 3I/Atlas's route intersected the orbits of Mars, Earth, and Venus in a sequence that seemed almost choreographed, maximizing its time within the zone of planetary observation. No other interstellar object, neither Oumuamua nor Borisov, had threaded the solar system's main traffic lane so closely. For those charting its course, the question was no longer just what 3I/Atlas was made of, but who, or what, had chosen its path. Size, in the world of interstellar objects, is rarely a subtle clue. For 3I/Atlas, every attempt to pin down its dimensions led to the same unsettling conclusion: a nucleus somewhere between 3 and 12 miles across, dense enough to shrug off the faint sunlight of deep space. Not a fragile cloud of ice and dust, but a compact, stubbornly bright core. Hubble's high-resolution imaging, paired with JWST's infrared readings, offered no hint of the sprawling, diffuse shells seen in most comets. Instead, the coma clung tightly to the nucleus, refusing to bloom outward even as the object drew closer to the sun. Photometric occultation studies, where the object briefly dims background stars, helped rule out a loose rubble pile. The dips in starlight were sharp, consistent with a solid or at least highly cohesive body. Reflectance curves, measured across multiple wavelengths, painted a picture of a surface more akin to a D-type asteroid than any known comet, featureless, red, and unusually uniform. No jets, no fans of gas, no evidence for the kind of outbursts that would scatter debris into a sprawling halo. For planetary scientists, this was like finding a bullet where they expected a snowball. The numbers didn't add up. A city block-sized object, travelling at interstellar speeds, yet showing none of the telltale signs of a loosely bound aggregate. The compactness suggested a hull, engineered or at least forged by processes far more intense than those shaping the solar system's wandering icebergs. Each observation narrowed the possibilities, leaving behind a form that looked less like a relic of cosmic chaos and more like the product of design. The question lingered: what kind of force could build something so dense, so resistant to the slow erosion of space? Power, in the vocabulary of comets, is supposed to be slow and diffuse, a gradual warming, a lazy release of gas. But 3. I/Atlas punctuated that expectation with a series of abrupt, blinding surges. Ground-based photometry and space telescopes logged brightness, spikes reaching as high as 1.2 magnitudes, each one flaring up in minutes, then vanishing without a trace of spreading dust. For reference, a typical comet outburst leaves a trail: jets of vapor, clouds of fine particles, an expanding haze that lingers for days. Here, the light came and went as if someone had flipped a switch. Multi-band light curves from JWST and Hubble confirmed the effect across visible and infrared wavelengths. Some spikes clustered at similar rotational phases, but others broke the pattern entirely, appearing at random. The absence of accompanying dust, even in the deepest exposures, ruled out the standard explanations. No jets, no fragments, no new debris. Models of surface ice cracking under solar heat failed to match the speed or intensity of these events. The colour shifts during each burst hinted at something more, a thermal signature inconsistent with sunlit rock or ice alone. Astronomers debated whether internal energy sources could be at play. Was heat stored deep beneath the surface, vented through hidden fissures? Or did these surges betray an engineered mechanism, reactors, batteries, or propulsion systems cycling on and off? With no dust tail and no gas emission to measure, the only evidence was the light itself, sudden, powerful, and unexplained. Each spike added to the sense that 3I/Atlas was more than a passive traveller. It was active, dynamic, and possibly alive with power. In 2017, astronomers caught their first true interstellar visitor, Oumuamua, Oumuamua. It arrived with no warning, a cigar-shaped enigma tumbling through the inner solar system, accelerating as it left, yet with no visible jets, no debris, nothing but a silent change in speed. The official explanation was a fragment of rock or ice, perhaps an exotic comet, but the data never quite fit. The mystery of Oumuamua faded into debate, unresolved but unforgettable. Now, less than a decade later, the pattern repeats. 3I/Atlas, the third object of its kind, enters the solar system with its own catalogue of anomalies, unusual chemistry, flickering lights, and a trajectory that seems almost too precise. For those who tracked Oumuamua, the sense of déjà vu is impossible to ignore. 2 interstellar objects, each breaking the rules in different ways, each arriving within a single generation of sky surveys. Not random, not routine, something more systematic, perhaps even intentional, is at play. Avi Loeb, the Harvard astrophysicist who first argued for an artificial origin for Oumuamua, has returned to the spotlight. In interviews and papers, he draws a line between the two events. If it's not a comet, it could be the first evidence of alien technology passing through the solar system, a historic moment. Critics call the parallels coincidence, a product of better telescopes and bigger data sets. But Loeb insists the odds are too long, the timing too sharp. Within a decade, 2 messengers from the stars, both refusing to fit the patterns of natural debris. The question, once whispered at the edges of science, now stands in the open. What if these objects are not just wanderers, but probes? The mystery deepens, and the search for meaning begins anew. If 3I/Atlas is not a product of nature, the implications reach far beyond astronomy. For the first time, the possibility stands before us. A constructed object, built by minds not our own, passing through the solar system. In the language of SETI, 3 archetypes haunt the literature: scout, beacon, relic. Each has a different purpose. Each would rewrite our place in the universe. A scout probe is the most active of the trio, an autonomous machine sent to map habitable worlds, analyze atmospheres, and perhaps even seed life. Its mission would be to gather data, moving from star to star, adapting and reporting back to its makers. The beacon, by contrast, is less about exploration and more about communication. It would transmit signals across interstellar distances, a lighthouse in the galactic dark, waiting for someone anyone to listen and reply. Then there is the relic, an artifact adrift for millions, maybe billions of years, its original purpose lost to time. It might be derelict, its systems long dead, or it could be a survivor, quietly running on reserve power, waiting for a trigger it may never receive. Physicist Michio Kaku has spoken to the gravity of this moment. If we confirm an object like this is artificial, it means we are not unique. The universe is seeded with technology, and we are only now learning to read the signs. The paradigm shift would be total. Every telescope, every mission, every theory about life and intelligence would need to be re-examined. The question would no longer be, are we alone? But what role do we play in a galaxy that builds and sends machines across the stars? Newsrooms around the world scrambled for headlines, each one more sensational than the last. Within hours, the phrase alien spacecraft trended across social media, outpacing even the most sober scientific releases. Hashtags multiplied, YouTube thumbnails flashed with images of glowing ships and cryptic question marks. The story had left the journals and entered the bloodstream of public debate. Network anchors called in experts to explain or to pour cold water on the possibility of extraterrestrial technology. Some outlets ran with the most provocative language. NASA's new data points to alien craft, while others tried to anchor the conversation with reminders of past false alarms. In the midst of the frenzy, the European Space Agency issued a statement. Unusual but natural. All available evidence supports a cometary origin. The wording was careful, almost offensive, as if anticipating the next viral wave. Neil deGrasse Tyson, never one to shy from cosmic controversy, appeared on late-night television with a warning. Extraordinary claims require extraordinary evidence. Right now, we have an extraordinary object. But evidence for aliens? Not yet. His words ricocheted through forums and comment sections, fueling both skepticism and hope. The conversation spilled into classrooms, cafes, and backyard telescopes. Citizen scientists logged their own observations, sometimes challenging official data, sometimes echoing the doubts of the pros. The debate was no longer confined to laboratories or mission control centers. It belonged to everyone. So, the question lands at your feet. Is 3I/Atlas a comet, or the first messenger from another civilization? The answer, for now, is still in orbit, waiting for the next discovery, or the next bold claim. 3I/Atlas is only the third interstellar object ever recorded, discovered on July 1st, 2025, traveling over 130,000 miles per hour and crossing within 5 degrees of the ecliptic, a statistical rarity of less than 0.01%. NASA and the European Space Agency data confirm an 8:1 carbon dioxide to water ratio, nickel and cyanide gases, and abrupt energy surges without a visible dust tail. The James Webb Space Telescope imaging shows repeating surface flickers, and reflectance studies indicate a dense, compact structure between 3 and 12 miles wide. Despite these findings, no peer-reviewed study has determined whether these anomalies are natural or artificial. Previous cases like Oumuamua in 2017 showed similar unexplained behaviors, making 3I/Atlas part of a growing pattern. Agencies acknowledge the unusual data, but stop short of definitive conclusions. As 3I/Atlas approaches perihelion, the world waits for answers. For now, the evidence challenges our assumptions about what can travel between the stars.
If the truth is hidden in the data, astronomers have months, not years, to find it. When Atlas disappears, so does the best chance to understand what's really moving through our solar system. The question hangs in the silence. What are we missing, and will we ever get another chance to know? On July 1st, 2025, the discovery of 3I/Atlas marked only the third confirmed interstellar object ever observed, instantly drawing scrutiny with its unprecedented 8:1 carbon dioxide to water ratio, over 6 times more carbon dioxide than any known comet. Raw data leaked from NASA archives revealed a dense gas veil blocking a direct view of the core, and spectral analysis confirmed nickel vapor and cyanide, signatures rarely seen together in solar system objects. Despite public statements from NASA that Atlas is natural, official documents and expert testimony highlight a pattern of anomalies: a city-sized mass, a spectrum unmatched by ordinary comets, and a trajectory from the ancient thick disk of our galaxy. Many scientific questions remain. Is the rainbow glow a natural effect or evidence of something engineered? Why does the core remain hidden despite advanced telescopes? As Atlas approaches perihelion on October 29, 2025, the chance to study these mysteries is closing fast. What lies beneath its veil remains unproven, but the evidence, now public, forces us to confront how little we know about visitors from beyond our solar system.